Hi everyone, my name is John Paul and today I'll be talking about NG Join, a scalable join for massively parallel multi-GPU architectures. This work was done in collaboration with Shengli Lu, Associate Professor Ping Shenha and Associate Professor Chu Tong Lau. So to begin with, multi-GPU systems have become popular in the recent years, with NVIDIA itself releasing multiple multi-GPU servers and workstations for deep learning and high performance computing workloads. The figure shown below corresponds to a DGX1 server from NVIDIA containing 8 V100 GPUs interconnected over QPI, PCI, and NVLink interconnects. These systems have enabled new opportunities for relational query processing, specifically due to their unified memory architecture and the use of newer, higher bandwidth interconnects. They have made it possible for GPUs to collectively process much larger data set than was possible by a single GPU. Further, this has also made it possible for GPUs to function as primary computing devices where the data is distributed across its collective global memory, and the entire pipeline of relational operators can be accelerated over just the GPUs as opposed to working as a co-processor to CPUs, accelerating a very small subset of the operations that can fit, whose data can fit within the GPU global memory. Now, efficient relational joins are key to any high performance query processing systems. To this extent, multiple implementations in the recent years, including DPRG and UMJ, have been proposed that are capable of joining the relations distributed across multiple GPUs. Due to the communication cost almost always being a bottleneck, these implementations work by first trying to partition the input data present locally at each GPU based on the same part based on a standard partition key. Now these partitions are then allocated to each destination GPU, and during the database data distribution phase, the partitions are moved to their allocated GPUs. This means that the join operation that happens after the data distribution does not have to cross multiple GPUs, and the data need not be pulled across the GPU interconnects. All the input relations can then be joined locally within each GPU, generating the output. Now, in spite of the attempts to minimize the communication cost, we find that existing implementations are highly inefficient on modern multi-GPU hardware. To demonstrate this, we present the execution cost per tuple for both DPRJ and UMJ when joining two input relations with the number of GPUs varied from 1 to 8. Please note that in this example, we use an input size of 512 million per tuple, and the final final cost is normalized to the number of tuples as shown by the y-axis. Now, as highlighted in the figure, the UMG implementation achieves no improvement in performance with the number of GPUs. In fact, when scaling from 1 to 8 GPUs, the UMG implementation encounters a significant degradation in performance, making them highly inefficient for modern multi-GPU architectures. Moving on to the DPRG implementation, we find that the implementation fares much better than the UMG implementation and demonstrates some improvement in performance with the number of GPUs. However, still, for an 8 times increase in the number of GPUs, the DPRG implementation achieves only around 2.13 times improvement in performance, making it highly inefficient as well, which means it achieves very low scalability on these modern multi-GPU systems. Now, this is because as the number of GPUs increases, the DPRC implementation spends a significant amount of time moving the data between the GPUs due to its highly inefficient data distribution phase. In fact, for 8 GPUs, the DPRG implementation spends 66% of its execution time moving the data between the GPUs, and is still only able to achieve less than 50% utilization of the GPU interconnects. Now, this high data transfer cost in UMJ and DPRJ are rooted at the unique hardware characteristics of modern multi-GPU architectures. Unlike distributed CPU systems, which often have a relatively homogeneous interconnection network, multi-GPU systems are interconnected by a set of highly heterogeneous links, as shown by the diagram on the left here. These links often have very different bandwidth, latency, and efficiency characteristics, as shown by the example figure on the right, which compares the bandwidth characteristics of both the PCIe and the NVLink interconnects. Further, other hardware limitations of GPUs, like its inability to sustain simultaneous data transfers over all its available network interfaces, makes this problem even worse. For example, even though GPU 4 shown here has 1, 2, 3, 4, 5 incoming outgoing network interfaces, it is not capable of sustaining simultaneous transfers over all these interfaces. Hence, a redesign of existing join implementations is necessary to make efficient use of modern multi-GPU architectures. So, as we mentioned before, existing join implementations need to be redesigned efficiently for these modern architectures. Now, when we began the task of redesigning existing implementation, we came up with three key design rationales based on which we would be redesigning the system. First, the design of the data distribution phase of the new implementation needs to completely move away from the highly inefficient static single hop data transmission policy in existing system. This is because this such an implementation assumes that the direct route between two GPUs is almost always the most efficient route. As you can, this is clearly not the case, as you can see from the figure here. For example, if you want to send the data from GPU 4 to GPU 1, the direct route over PCI is not the efficient route. The route over NVLink over GPU 0 is a much more efficient route for this data transfer. Second, we to maximize the overlap between data transfers and to make efficient use of the communication hardware, we need to adopt a more fine-grained packet-based data transfer approach. Finally, we need to avoid reinventing the wheel and reuse existing techniques, evaluate existing techniques and use the ideal ones, especially for the compute phases where the implementation need not be changed completely. Based on these three key design rationales, we designed MG-join, and overall MG-join consists of 4 execution phases. The histogram generation phase, where a histogram is generated to determine how the data will be partitioned across the GPUs. Then the global partitioning phase, where the data is first partitioned locally at each GPU and then distributed over to its destination GPUs. This means that the global partitioning phase also includes data distribution, where the data is moved between the GPUs. Finally, then comes the local partitioning phase, where the data is further partitioned into more fine-grained partitions to improve the performance of the probing stage. And finally comes the probing stage, where the data input relations are actually joined. The novel contributions of this work are mostly on the data distribution phase, and hence in this presentation I'll be focusing on this phase. For the details of the improvements across other stages, please refer to the original paper. Specifically, to improve the data distribution phase, we first adopt multi-hop data transmission and then improve upon this by adopting an adaptive data routing policy. We will talk about each one of these techniques in the coming slides. So first, multi-hop data transmission involves moving the data from one GPU to another over other intermediate GPUs. For example, in this example given here, this would involve moving the data from GPU 0 to GPU 2 and GPU 3 over intermediate route GPU 1 instead of the direct route available between the two, if any. However, the challenge with implementing such a multi-hop implementation is that there is no inbuilt support from the GPU firmware for this kind of multi-hop data transmission, and implementing it at the application level is challenging due to the need for allocation of additional routing buffers at intermediate GPUs. This is problematic because the more intermediate buffer that is allocated for the data transfer from, let's say, GPU 0 to GPU 2 at GPU 1, the lesser the amount of memory available for GPU 1 to perform its own join operation, which can lead to severe performance degradation of the overall join operation. Second, when each GPU is free to route its data over other intermediate GPUs, it needs to synchronize with all the other GPUs to avoid conflict, leading to very high synchronization overhead. Because if not synchronized, the GPUs could end up overwriting the intermediate buffers at the destination, leading to errors in computation. So to minimize the in these impact of these inefficiencies, we adopt a fine-grained packet-based implementation. This prevents intermediate GPUs from getting overwhelmed by large data transfers from other GPUs. Further, we make use of circular reusable buffers. Now, reusing buffers will add to more, will require more synchronization. However, to minimize the overhead of the synchronization, we allocate distinct circular buffers for each source GPU at every one of its destination GPUs. This means that, let's say, when source GPU 0 wants to send a data to a buffer in GPU 1, it only need to synchronize with itself because that buffer is allocated just to GPU 0. So that single circular buffer that is available at GPU 1 would be exclusively allocated to GPU 0. Further, in addition to this, the entire route for each packet is embedded in its packet header, and an intermediate GPU does not need to synchronize with the source GPU to determine the route. Each GPU picks up all the packets arriving at its incoming queues and either unpacks them if they're destined for that GPU or simply forwards the packet to one of its outgoing queue based on the packet header. While multi-hop routing does help improve the performance over existing single-hop strategies, it still cannot fully resolve the congestion in certain interconnect links due to the highly dynamic nature of the join operation. This is because the route between each pair of GPUs will still be determined statically in existing implementation. To show the problem of determining the route statically, we present the cost of the data distribution of three different static routing policies: bandwidth, hop count, and latency. When the parameters such as the hardware configuration, the packet size of the transmission, and the skew in the distribution of the data is varied. So on the figure on the right, this shows the packet size and this shows the level of skew according to a SIP of distribution. Now, the bandwidth policy adopts the route that maximizes the bandwidth between the source and the destination, while the hop count and latency static policies chooses the route that minimizes the hop count as well as the latency. Now, as shown in the figure, you can clearly see that these factors such as the hardware configuration and the input hardware and input configuration can have significant impact on the choice of the optimal routing policies. Now, since these factors can only be determined at runtime, and there is no clear winner among the static policies, an adaptive routing policy is essential to designing an efficient data distribution phase for multi-GPU architectures. Now, determining the optimal route at runtime through exhaustive search is still not suitable. This is because this problem becomes similar to the multi-commodity flow, which has a very high cost when solving even for a small number of GPUs. Hence, MG-join uses a heuristic-based adaptive routing approach. For this, we use something called an adaptive routing metric or an ARM value. The ARM value combines the impact of both dynamic and static characteristics of a network, and this value is computed for each source destination pairs. Then every time a packet needs to be transmitted from the source, the packet is assigned the route with the lowest ARM value to the destination. Unlike an exhaustive search that requires all GPUs to synchronize, the ARM metric of each route is computed at each GPU independently. To enable this, each GPU broadcasts the delay encountered by the packets passing through it to every other GPU in the network. This means that every GPU is aware of every other the delay or the queuing delay in every other GPU and for every other route. Now, when a GPU receives a broadcast asking it to update one of the parameters, it would update these parameters used to compute the ARM value, and the remaining packets would be routed based on the new value. This means that, as an example, let's say there is a severe congestion in one of the nodes. The node would broadcast and update everybody saying that there is a significant increase in the queuing delay at that node. Then every node would update it and the remaining packets will be redirected along a route with a lower queuing delay. Now, for experiments, we use two multi-GPU hardware The first one, a DGX1 server from NVIDIA, and the second one, a DGX station workstation from NVIDIA. Each of these contain 8 and 4 V100 GPUs respectively, while each of these V100 GPUs have 32 gigabytes of high bandwidth memory operating at 900 gigabytes per second. Or these GPUs, each of these GPUs also supports NVLink and PCIe interconnects. Or further, for comparison against CPU, we use a dual socket Xeon E5 2698 V4 CPU with 40 logical cores operating at 2.2 gigahertz. System is also equipped with a total of 512 gigabytes of main memory. As workload, we use 8-byte tuples with 4-byte keys and 4-byte values. The values are generated sequentially, first generated sequentially and then shuffled randomly. We vary the input size from 512 million to 4 billion tuples for the experiments, covering a broad range of input sizes. As part of evaluation of MG join, we first evaluate the benefit of simply using multi-hop transmission strategy over existing single hop transmission strategy. And as shown in the figure, you can see that simply by adopting multi-hop data transmission, MG join is able to improve the performance by up to 2.35 times over DPRJ. Now, this does not include the use of adaptive routing, and this is simply coming from the use of multi-hop routing strategy. Finally, the ARM value based routing adopted in MG join outperforms routing based on other static policies by up to 5.37 times, as shown in the figure. Overall, the use of both adaptive and multi-hop data transmission together helps MG join to achieve over close to 97% utilization of the GPU interconnect network, while implementation such as DPRJ is limited to a little over 30%. This means that our implementation is functioning at close to optimal levels of the network interconnect utilization. Finally, the techniques proposed in this paper helps MG join to achieve over 7.2 times performance improvement over UMJ and DPRJ. Further, while UMJ and DPRJ achieves very poor scaling over with the number of GPUs, MG join is able to achieve close to linear scalability. To further demonstrate the benefit of MG join, we compare a query processing system which makes use of MG join against a query processing system that makes use of DPRJ, as well as the state-of-the-art commercial GPU database system, which is OmniSky GPU. We also compare the performance against CPU version of OmniSky to understand the performance of GPUs relative to CPU implementations. Overall, MG join achieves over 4.5 times performance improvement for the 6 TPCH queries shown in the diagram below. Finally, MG join also demonstrates the lowest degradation in performance when with skew in input data size, and also shows good scalability with increasing input data size. So to summarize, efficient join implementations are key to taking advantage of modern multi-GPU architectures for query processing. However, existing implementations encounter high communication overhead and poor scalability when executing on modern multi-GPU architectures. To address this, we propose MG join, a novel implementation making use of adaptive multi-hop data routing. MG join, by taking advantage of techniques proposed in the study, MG join achieves up to 7.2 times performance improvement over existing implementations. Finally, in this work, we simply explored optimizing the join operation for modern multi-GPU architectures. Optimizing the entire query on multi-GPU architectures and efficient use of these architectures as primary computing devices are still open questions. Further, with the newer and faster interconnects, communication might not be the biggest bottleneck for many operations in the near future. So optimizing for the new bottleneck is also an interesting future direction. Thank you.